Welcome to solverfy.
We're given a weighted graph, and we're asked to use Kruskal's algorithm to find a minimum spanning tree for this graph. The graph is the one from exercise 4 in the book. This is a graph on vertices A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P with weighted edges. So I'd refer you to the book to see the vertices with their weighted edges. I have not drawn the weighted edges. It's too complicated, I feel like. But an accurate picture is in the book. And to use Kruskal's algorithm, what we're going to do, the first step is to simply draw the graph which has the vertices of our weighted graph. So I've drawn here vertices A through P. The next step in the algorithm is to find the edges with the smallest weights. So the smallest weights in the given graph is 1, and this belongs to the edges AB, AE, CD, and DH. So first let's add AB. We don't create a circuit, so this is valid. Let's add the edge AE. We don't create a circuit, so this is valid. Let's add the edge CD. This does not create a circuit, so it's valid. Add the edge DH. This does not create a circuit, so it's also valid. Now, in the remaining graph, the smallest weight is 2. And so we want to consider all the edges of weight 2 that don't cause a circuit to be added to the graph. So first consider, say, edge AM. If we add AM, we don't cause a circuit, so this is valid. Though it's going to be a little bit hard to see the edge AM. Now if we add edge BC, we don't create a circuit, so this is also valid. If we add the edge DP, this doesn't create a circuit, although it's a little bit hard to see here. And so this is valid. If we add the edge EF, this doesn't create a circuit, so it's valid. If we add the edge EI, this doesn't create a circuit. If we add the edge GH, this does not create a circuit. And if we add the edge LP, this doesn't create a circuit either. And in fact, we can also add the edge NO, or MN, I mean. This is valid. We can add the edge NO. Still doesn't create a circuit. And so now we still need to connect vertices J and K to the graph though. And to do this, notice that the smallest weight of an edge connected to J is 3, and the smallest weight of an edge connected to K is 3. So for each of J and K, we're going to choose one of the edges with weight 3 incident to the vertex. So for example, IJ has a weight of 3, and if we add IJ, the graph is still not containing a circuit, so this is valid. And KL has a weight of 3, and if we add edge KL, we don't create a circuit. And now we see that we have a connected graph, and so the algorithm terminates. And therefore, by Kruskal's algorithm, follows that this weighted graph is a minimum spanning tree with the edges AB, AE, AM, BC, CD, DP, DH, IJ, KL, LP, MN, and O. And we also have EF and EI, as well as GH. So these are all the edges of the minimum spanning tree for this weighted graph. Now, we saw earlier in exercise 4 that we used Prim's algorithm instead of Kruskal's algorithm on the same weighted graph. And we see that using Prim's algorithm took much longer compared to using Kruskal's algorithm. Kruskal's algorithm had fewer steps. So again, we have a case where, for a given graph, Kruskal's algorithm was much faster than Prim's algorithm.